Okay, what I want to talk about is Professor Hiley's mention of Fritz London, and that the 1927 paper of Fritz London was the inspiration for Dirac's creation of the standard ket. And all this stuff seems really abstract and obscure, and it is, but what we're talking about is the foundation of reality as defined by science. So that's what this video is called, Understanding the Nature of Reality. Most of it is the talk by this neuroscientist who worked with Bohm, and then he co-published with Basil J. Hiley, but Basil J. Hiley steps in and makes a commentary about starting around 50 minutes in, and that's where he starts talking about
you guys have put on it. And I pointed out that
he gets upset.
Sorry?
Bohm himself used the term, but then
he gets upset about the Schrodinger wave function and this idea that Bohmian physics is based on a hidden variable, which he says was never true. And Pavel says, well, Bohm even used that for the title of his paper, and Hiley's like, well, no, actually the original title did not have that did not say hidden variable. And he doesn't know why Bohm's, had the title changed to hidden variable. And
I guess regretted.
Oh no, but we don't know why he used the term, because I didn't discover the first draft of his 52 paper, which didn't have the words hidden variables anywhere in the title. And I only wish he'd published it in that form, and we would have saved 25 years of argument. I'm sorry to be a little bit angry about. No, you know what I mean. I think I don't know how to get this across. We got to drop this idea that it's got anything to do with hidden variables, even the 52 paper, because it's as I showed yesterday, it's simply a unitary equivalent picture to the Schrodinger picture.
So, okay, so it's early in here where Hiley's trying to convey to Pavel, his co-author. So he's trying to get across like the serious core of his concepts in his research.
Him, on the other hand, and I think what has gone wrong, particularly in the field of philosophers you mix with, is to try to think of the wave function as something ontic.
Right.
And it isn't something ontic. And if you do, that's why we have all these problems. This had almost a century, and we're still trying to solve the problem of the collapse of the wave function. There is no wave function to collapse. And the reason why the wave function has this subjective, objective feature in there is because it is an algorithm. Because we're not following the dynamics in the mathematical sense. We're following an image of it. And I made this clear yesterday, Pavel. I'm sorry you were unable to go, but I understand.
The Bohm theory, and he's thinking in the early days when
Supporting him, on the other hand.
Intuitive sense. Yes, but
feature in there is because it is an algorithm.
Okay.
Because we're not following the dynamics in the mathematical.
Okay.
So where do I start with this
we're going to go a bit earlier.
Yesterday I did present very much some ideas on how we think about movement, how we change from the idea of particles being little billiard balls into something where a particle actually has an extended structure, and that extended structure comprised energy, because I don't know how else to talk about it, and that energy is the individual, but the energy is not point-like. The energy actually extends over a region. And I did give a little picture, the best you can do, of the Gaussian blob that I ended up my talk with giving, showing that you can think of the energy as centered on some mean position, but it actually extended over a region which both Giuseppe Vitiello and I were trying to call, in my case, x and x prime, in his case, x plus and x minus. And this really is to give rise to the way the process is unfolding. The process is unfolding not along the individual line, but it's much more general. It's the mean value that is following the line of those trajectories that you showed again. And that is really where you summarize, this is the individual. But now within that individual, there is a process going on which is not a local entity. And I back this up with the idea that when the high energy boys look at the structure of a proton, for example, instead of seeing it as just 3 valence quarks, as we thought originally when the idea of quarks was first mooted, but we find now that there are only 2% of that proton are valence quarks, and all the rest is this bubbling sea of quark, anti-quark, creation and annihilation. So it really is active, so that you really can't pin the thing down in a particular way as we would love to do and play quantum billiards. It doesn't work that way. Okay, but then already I think you can see I'm struggling for words as to how to get this idea across. And again, I think I'm going to talk about some new work that Maurice de Gosson in particular has brought to my attention, which I think is very important and which I didn't mention in my talk at all. And that again stems from another theorem. As you can see, as people who are listening to me yesterday, theorems are very important in punctuating the way you think. And I know theorems are always very suspicious things to look at, because sometimes you put assumptions into the theorems which are wrong. But I don't know how else we can progress. So what is this theorem? This theorem was a rather remarkable theorem. First of all, what we find in the way we describe classical mechanics, for example, is that we can redescribe the position of momentum. We can make transformations on the coordinates of position and momentum, and we can actually turn position into momentum and momentum into position. And we still find the unfolding is exactly the same. So the unfolding is the invariant under change of coordinates. And that's essentially the principle of covariance is summarized in that idea. So we've got to be a little bit careful. What are we actually talking about? Are we talking about P's and Q's as what is actually going on? Or are we using our P's and Q's somehow to let us find what the invariants of the movement are? And then it's the invariants of the movement that are, if you like, the real things. So it's not the particle with a position of momentum moving. It's rather with these variables, we can construct an object, let's call it an object, which has not a precise definition as a point, but rather an extended structure, so that the energy that's involved in that process of that particle is actually not localized at a point. And that's essentially what I mean by non-local energy. But I also get the non-local energy from many of my discussions with or reading of Roger Penrose's ideas. Because he is very clear that even in the classical domain, it is not easy to see what you mean by a particle. How do you distinguish the particle from the void? And in the last slide I think I gave yesterday, excuse me if my memory is not very good now, but I think what I showed was the London's work. I don't think you know about this paper, Pavel. I don't know if I sent it to you. But I discovered a 1927 paper by Fritz London, who was really one of the guys who gave us liquid helium and superconductivity. He was in on the early days when he was establishing those ideas. And there he shows that and what I did was to show how the Bohm theory actually supports his idea that it is not possible to distinguish between the material substance and the void. There was some sort of, and that's why I say that's the way I'm trying to talk about it, is the blob, because that seems to be.
Okay, so he's referencing Fritz London. He said it was in his talk from the previous day. Okay, so that means we got to go to his talk from the previous day.
A way of indicating something which is not very precise. So I don't think things have to be precise. And I'm wondering whether if we really had the classical world as we would like it, it would be a dead world in which no evolution is possible. No movement is possible. Because remember,
he's getting into biology right there. That's what I've been trying to tell him about the ecological crisis. I send him emails about that. So that's
back to Zeno. Zeno was very worried. How on earth do we understand giving a particle a position and yet giving it a momentum, giving it a velocity at the same time? Now, what we did in our mathematics was to say, okay, well, we can define the velocity as the difference in 2 points divided by the time it takes to straddle those 2 points. And then what we find is that, and London brings this out in that paper very, very well. This is 1927. And this is where I think Dirac got his idea of unfolding, because he has it in his book as well.
See? So he says that Dirac got it from London.
And I think David Bohm picked that up and developed it
and then Bohm got it from Dirac.
In his particular way, to show that these are not Emmett railway lines that the particle is chugging along. It is an actual unfolding process. Now, how do you keep the damn thing together? If you've got this vague idea that you've got the derivative is no longer continuous along these trajectories, Bohm makes them continuous by a very subtle averaging process. But how do we keep the thing together if it's more like something like a fractal movement or a Brownian motion movement that is actually the underlying process?
So Hiley actually asked me about this when I referred to Alon Kahn's talk discussing von Neumann.
What one finds, and this is the theorem I'm struggling to get over across to you, and that is the idea of the no-squeezing theorem, Gromov's no-squeezing theorem. Now that actually tells us that if you start off with something which...
Okay, so let me look for, this is a month ago, I'm going to look see if we can find his talk from yesterday. I just want that he says was done yesterday. I just want to see if he talks about that Fritz London thing more. So a month ago. It would have been just a Basil J. Hiley talk a month ago. He said yesterday. Here we go, Basil J. Hiley. So this must be it. Oh.
Hello everyone, welcome to the second weekend of Beyond Bone, Science, Order and Creativity, Physics and Metaphysics. I'm James Barbieri, Program Director of the Corey Center, and I'll be your host for today. And as a host, I'm here to help you throughout the call, so any problems, technical or not, feel free to just send me a message in the chat. Before we begin, I'd just like to...
Wow, I don't even think I've seen this one yet. Oh. Okay. Cool. Alright, so this will be good. Let me get to the end of it though. I'm just looking for that. Right, so this is what I've been saying from the future and from the past. Gauge fields. Alright, I'm just going to go to the end to see if he discusses that Fritz London 1927 paper. Here it is right here. Fritz London. Take this off. In the Weil theory, one could justifiably think that in an empty space the measure could be influenced only by the electromagnetic field. One must now take into account that the old distinction between impenetrable matter and the void is removed. Yeah, that's the quote. I already found that quote. I read the paper, so let me see.
London did actually get round the difficulty that Einstein objected to with Weil's phase, and what he says here then is, in the Weil theory, one could justifiably think that in empty space, the measure could be influenced only by the electromagnetic field. One must now take into account that the old distinction, I hope I can read this carefully, the old distinction between impenetrable matter and the void, and please, the English translation has got this word wrong. This is Greek for void. It's got a new at the end there, which completely threw me. So and the void, is completely removed, and that one is always in the interior of the all-pervading new substance. And he was looking at the wave function as the substance. So this is the wave function, if you're using it in the old language.
Good morning.
This is the old language, and sorry, good morning to whoever that was who interrupted me. There's something going on in that space. So already in 1927, we had this idea of what was going on in the space. Okay, now then, just final slide before I come to conclusions.
Okay, so I want to go back to this 1927 Fritz London paper, and then I'll have to return to this talk by Hiley. I'm surprised I haven't even listened to this whole talk yet. But he's going back to Du Bois' research, because that's what the Fritz London paper is also relying on. And so before, obviously, we'll have to watch, whoever's watching me, they can watch. I'll link this in the video, this Hiley talk. So now we're going to go to the Fritz London paper. Actually, I did a blog post on this, so let me just go to my blog post. So again, that commentary first said is that the unfolding is the invariant behind the principle of coordinates, so that's a noncommutative unfolding. An extended noncommutative structure is a non-local extended energy. And so he's saying things don't have to be precise. This was the big emphasis of my own quantum physics professor, is that the foundation of reality needs to be accurate, and accuracy is more important than precise. And so our science has been very precise, but it hasn't been accurate. And then Hiley makes the point that if we take classical physics seriously, it would mean we live in a dead world because of this no movement from Zeno's paradox. And that's such a profound point. I mean, he's criticizing our whole modern science paradigm right there and how it's causing the ecological crisis. He's not saying, he's saying there wouldn't be any evolution. So that's what that comes down to. So again, he's saying that Fritz London first captured this problem of quantum physics that Einstein was discussing, and that Dirac got his concept of unfolding and enfolded, and David Bohm picked that up from Dirac, but it originated from this Fritz London paper. And so because of quantum physics, the derivative is no longer continuous, so you have to redefine space-time. So calculus is not the foundation of reality, contrary to what everybody's taught. And so then he gets into the Gromov no squeezing theorem, which I'm not gonna. Well, he just points out that as of now, they're just assuming that h bar will reduce to 0 as the derivative, but when you do that, you get a infinity divergence, quote unquote. The whole thing blows up, and so this is the problem that Feynman and Dirac tried to fix. But Basil J. Hiley's big point is that you shouldn't try to reduce h bar to 0, but rather you have to operate from the second derivative or second order of h bar squared. And then within that, you have two momentums of energy for each particle. And that's that deeper noncommutative process. And so he's saying that this is a dynamical mathematics because it's from the future and the past, literally in the physics, and it's non-local, so it's inherently entangled. And that's what the algebra is telling us in the metaphysical sense. Okay, so now we get to the Fritz London paper from 1927. So Fritz London, he's pointing out that that you have the whole number multiples of Planck's constant as the period, and that's from de Broglie. But this gets serious when you talk about the radical continuum conception of matter, based on the calculus and magnitude as symmetric commutative geometry. So in quantum physics, the solution of the discontinuously bounded electron then has to vary continuously in space and time. And so that's the paradox that Einstein was having a problem with about quantum physics. And so then, because the discrete particle of the based in the quantum, from Planck's constant is, as the period of the particle is then oscillating in an infinitely bound medium, then you don't have the discontinuities and they can't be understood, nor rigid bodies that permit one to establish a metric. So this is the whole quantum measurement problem that Sir Roger Penrose also focuses on. And so Penrose's point is we need to get beyond this problem, somehow beyond quantum physics. And that's Basil J. Hiley's point, is that the non-commutativity is how you do that. And so originally on this paper by Fritz London, he's saying if you rely on Weil's theory of space, then you can try to solve this problem. And So what's really fascinating is that Fritz London says, I'd like to pause to discuss here whatever it should mean that every line segment is regarded as a complex quantity. And so then, you have to present the change in the phase while preserving the absolute value. So that's what quantum physics does, is they square that complex value to get the location of the particle as the amplitude squared, and that's where you lose this change in the phase. That would be a negative frequency and a time reversed non-locality. And quantum theory allows matter to have only a discrete series of motion, and one suspects that those distinguished motions will allow one transport to gauge only in such a way that the phase will have made precisely a whole number of circuits. So that's the noncommutativity, is you have this discrete phase that is the metric as the yardstick. Such that despite the non-integrability of the transport of line segments, the gauge will always be realized in a single valued way at every location. In fact, one recalls the resonance property of the de Broglie waves, which is in the same way the older Sommerfeld-Einstein quantum condition first reinterpreted, and so by de Broglie so successfully, that it is generally coupled with the phase velocity. So he's pointing out that when it's a 5-dimensional wave function, then you can average out the superluminal phase with the group velocity, and you get the speed of light as the 5-dimensional wave function. Now, Basil J. Hiley's big point is that you can't do that within space-time, because then you would have to say that the photon has a rest mass, when in fact we know that the photon has a 0 rest mass. And so if you are assuming that the photon has a rest mass, then obviously you get a singularity as an infinity that doesn't work mathematically. And that's why you cannot reduce Planck's constant to a 0 value. And you have to, and so what that's why Feynman and Dirac and Feynman developed renormalization by assuming a change of mass. But what Basil J. Hiley is saying is actually due to this quantum potential that's not local, that Bohm discovered, and it's precisely this difference between the real and imaginary that Fritz London also points out. So where did I have that? It's right here. Okay, upon splitting into imaginary and real components the Schrödinger wave equation, in that representation one recognizes the counterpoint to the de Broglie theory. And this is exactly the same thing as the standard ket that Dirac later developed, that depends on the direction of the algebra. It is also be obvious that we're dealing with the problem with two unknown real functions. So this is the hidden noncommutativity as the quantum potential that is derived from splitting the complex wave of the Schrodinger wave into the imaginary and real components. And so this is exactly what David Bohm did to discover the quantum potential. So it was already, Fritz London had already done this originally in 1927. And so here's the quote. So then Basil J. Hiley has this quote in his talk. Matter which is banished from the field behind impenetrable boundary surfaces or relegated to its singularities in its electron theoretic conception is now spread out over all of space. And he has a footnote in here where he explains that that's due to this wave equation. It's a, what do you call it? It's I can't remember, but it's a standard. It just causes it to be a superposition that's non-local. Whereas in Weil's theory, everyone has a right to imagine that a yardstick in empty space is influenced by only the electromagnetic potentials that prevail there. Again, that would be the noncommutativity. One will now have to account for the fact that the older separation between impenetrable matter and the void has vanished, and one will always find oneself in the interior, so to speak. So this is the big point of David Bohm and Basil J. Hiley as well, that in quantum physics you no longer have this separation of matter with some kind of external objective spacetime, because you have this inherent non-local time and frequency process going on. So he's saying that Fritz London figured this out already in 1927. Of course, he doesn't, explain it really clearly because he's still, just discovering the concept. So in this 2016 paper, Hiley had cited Fritz London's 1945 paper saying the local mean velocity has no true quantum mechanical significance since it cannot be expressed as the expectation value of any linear operator. And so this is, okay, in other words, it has been excluded on the grounds that it does not fit into standard quantum mechanics. In this paper, we have shown that the standard quantum formalism is a fragment of a larger non-commutative algebraic structure. So basically, they're able to derive the local mean velocity by focusing on this deeper truth of the non-commutative time and negative frequency. And that truth is found in non-Western music theory as well. And so that the other thing, okay. So here's the other quote that I wanted to have from Fritz London's 1927 paper. He says it's not the magnitude but the direction as time that is changing. So when you have momentum, the definition of momentum is based on both magnitude and direction. So that's precisely the same as music theory, because again, if you have a perfect fifth in pitch, the 3 is the same magnitude, but the direction of the time is changing when you have it as a fraction. So you have 2/3 as the undertone, which would be C to F, and then 3/2 as the overtone, which would then be C to G. In other words, you have the same magnitude of 3, but since you're changing the direction in time as time and frequency, therefore it's non-commutative and has to be a different pitch in relation to the same point of zero space-time. In other words, the 0 to 1 symmetric gauge of for the magnitude, or what's also called the root tonic or home tone in music. And this is what had to be covered up by Philaeus, because he had to use two different values for the 0 to 1. In one case, he used 0 to 12, in the other case, he used 0 to 8. And I go into the details of that in my peer-reviewed paper, so it's going precisely back to this exact same problem. So to quote Fritz London, if one wishes to assume that it has any influence on the gauge at all, then it can depend only upon the magnitude of the four-dimensional displacement of the line segment, but not on its direction. So in other words, the gauge has to be maintained the same. Again, back to the music theory example, it would be 3. It's maintained as 3 in both cases, but the direction changes because in one case it's 2/3 and the other case is 3/2. And that's what Aloncon calls 2-3 infinity. So he's using precisely that same example from music theory. And so that's what I discovered on my own is in high school was this exact same concept that's now been rediscovered in quantum physics. So in other words, when de Broglie was trying to convert momentum and wavelength to time and frequency and the relation between the two, Heisenberg discovered it's the order of the frequencies that matters. And so you end up having this inherent non-commutativity to the frequency, which of course is also the truth of non-Western music theory. And then you have this inherent non-local foundation of reality that's an active information, or what they're calling proto-consciousness. And it's not a materialistic medium. Okay, so to quote Hiley again, however, we are talking about a single particle, and therefore such an approach requires the existence of some form of subquantum medium, an old idea which has dropped out of favor. In our approach, the two momenta, left and right direction, arise because the order of succession is vital and gives rise to a non-commutative structure. In such a structure, it is necessary to distinguish between left and right translations, and it is this difference that gives rise to the strange features of quantum processes. And this is what Hiley calls a new concept of motion, and that's why he prefers the term process, because motion implies some kind of matter, but this is before matter exists, and so it's just pure energy. Notice that in a non-commutative structure, a key factor is the recognition that we must distinguish between left and right translations. In other words, order is vital. The distinction gives rise to the possibility of a new type of motion, namely that an old structure may evolve into a new structure via the inner automorphism. So that's referring to what they call the diagonal in the matrices mathematics. So then he's quoting Heisenberg again, who made this discovery when analyzing the Ritz-Rydberg combination principle, and Heisenberg had to replace the original Ritz-Rydberg combination principle with a 2-index symbol. So when we think of this 2-index symbol, again, we can refer to music theory and realize that you have a ratio of 2/3 or 3/2, but you have to double the variables. So when it's 2/3, it's C to F, and then when it's 3/2, it's C to G. So you have the same thing here. We have a intermediary variable between the two, so they would both be the perfect pitch, perfect fifth, but they have a G and F between the C value. So of course that would be a linear frequency, but when you're converting it to position and momentum, then you have to convert it to a polar coordinate for angular frequency. And so the Planck's constant is actually derived from this direction of the order of the overtones, as Heisenberg called it. Okay, so I mean, I can't like precisely convert that to music theory, but it's the same concept. Okay, so that's pretty much it. And it's amazing to me that the very foundation of reality goes right back to this simple distinction between direction and magnitude of the momentum, and how that's the conversion of time and frequency is the difference between direction and magnitude as momentum of the wavelength. Yeah, it's weird. It's a very weird little catch-22 at the very foundation of physics from music theory. And of course, he doesn't directly connect it to music theory, but they kind of intuitively realize that it has to do with the future and the past of listening in music. They talk about that, so they realize there is a connection there. So you could say like this is 3/2, and then this would be, or this is 3/2, and then this is G and F. So you have the 3 and 3/2 and 3/2, and then G and F, and then that would be the perfect fifth. Something like that. Anyway, yeah, that's pretty fascinating. Okay, so we'll leave it at that. Oh, this is the paper I was quoting from, which is on Professor Hiley's academia site. Okay, so quite a bit of his stuff got posted on here. If you look on my site, you can see I get people reading my research from all over the world. Sweden, Serbia, Croatia, whoever's watching this, maybe you're on there. India, Taiwan, Barbados, Italy, Poland, Singapore, Canada, and so it goes. That's just in the past couple of days. So it's kind of fun that you get such a wide variety. So I posted this new paper, and so that's why I get more interest today. 80 views today because I posted this paper. Okay. Now my claim is that there might have been a cover-up with Bryce DeWitt's anti-gravity research, because Basil J. Hiley was wondering, because Bryce DeWitt discovered the quantum potential that's a gravitationally repulsive non-local force, but then Bryce DeWitt got sidetracked about it, and Basil J. Hiley couldn't figure out why. And my claim is, well, it could have to do with Bryce DeWitt getting into top secret anti-gravity propulsion research. But I don't know that. It's just kind of a fascinating little yeah, I already did a video on that. So anyway, if anybody's survived my video, thanks for listening. I also like that Fritz London has these Greek quotes, and then Basil J. Hiley appreciated that too, because he's like, it doesn't translate into English, so you have to. He's like, he said that the word void in Greek has an E at the end of it, and he thought that was interesting. So I guess he thought it wasn't quite translated as void from the English. I think that's not an E. I don't know what he meant by that. He said V. Yeah. Anyway, let's see what that I can plug it into Google Translate maybe. Okay.